have D-Brain's very own Gonzalo Uribarri, who will be talking about discovering features of Parkinson's disease and MEG recordings.
Thanks. Thanks first to the organizer for giving me the possibility to show our work here. I'm Gonzalo, and I will present work that we have done here in KTH alongside with Eric Francian. So I will be talking about subjects with Parkinson's disease and how to detect features. So our goal in our work is try to identify features that differentiate healthy controls from patients in Parkinson's disease. Ideally, we would like those features to be explainable, features of the data to be explainable, because at the end of the day, we want to come back to people doing modeling and clinicians and be able to learn something out of the data, not only like classify the data, but learn something. And in the long term, the idea is help in diagnosis and prognosis of the disease, and also help to learn what are the mechanisms of the evolution of the disease. So the outline of this talk, I will start describing the data we use. We have data from healthy controls, also from patients with Parkinson's disease. So Parkinson's disease is it's a disease that has some motor and cognitive symptoms on the patients that evolve along with the disease, so it gets worse with time, and it has a high incidence in the population, and it's getting worse because also we are living longer, so this is more prevalent on older people. And in this experiment, we measure data from patients and controls, and we measure MEG and eye tracking data. And so I'm lucky that I'm the last one, because Julia already introduced very nicely what MEG is. So I will talk now about the experiment the subjects do. So it's a saccade protocol. And this is a very simple visual task in which the subjects are looking at the target and they are waiting the screen for the target to move, then the target moves. And depending if it is a pro-saccade or anti-saccade task that the patient or the subject is informed about that, they have to move along with the target or in the other direction. It's a super easy task to do. And we are measuring how they perform the task with the eye tracking device. Surprisingly, the anti-saccade task, even healthy controls, we sometimes make mistakes because you have to be inhibiting your eyes not to follow the target. So around 20–30% of the times you also make mistakes with the anti-saccade task. So we will focus on recordings that are in the preparation phase, and we call the preparation phase to the phase before the target moves. So we will not look at the measurements when the target moves and when you follow, but to that particular phase in which you are waiting for the target to move. So you are concentrated, you are trying to perform well the task, and you are waiting for the target to move. And in the case of the MEG recording, we will take 1 second recording before the target moves. And in the case of the eye tracking, we'll take 1.5. So a little bit more about the dataset. The dataset was provided to us by people from MEG, from Mikkel and Daniel, and also the people that were working with the patients and the health controls were from Karolinska Hospital, Josephine Amper. It's composed of 55 subjects. So we have 28 patients with Parkinson's disease that don't have dementia, and the stage of the disease varies along this group. So we have patients that are very early stage and up to more middle stage or disease. And also we have 27 age-matched healthy controls. And there are around 100 trials per subject. So the subject go there and perform in sessions the experiment, and so they make several trials in one session, then they have another session and they make several trials. So the MEG data is reprocessed and source localized in 70 cortical regions of the brain. We use like an atlas, that's a conventional atlas of the cortical of the brain, and we have these 70 cortical regions. So we will map the activity, the average activity of those different brain regions. So just to this looks messy, but it's intended to look messy because we have a lot of data. This is data for 1 second of recording, and we have 70 brain regions. So this is each of these time series is the average activity on that brain region, and we have 1,000 points because we have 1 kilohertz of sampling frequency. So each of those trials, it is composed by 70,000 values, different values. So the task that we want to perform is being able to classify, looking at those trials, if those trials belong to someone with Parkinson disease or belong to a healthy control. It's a small, a single second of brain activity. We have a lot of data there, and we will try to classify looking at that. In order to do that, we will try to solve this using machine learning. But there are some challenges because using machine learning for a diagnosis of neurodegenerative diseases is not easy. There are several challenges here. The main one is that it's very hard to generalize to new unseen patients. So once you have trained your algorithm, for example, to classify your trials, then if you take another subject that it's not on your training data, it's very hard to generalize. And that happens because of a series of different reasons. And the most important are that usually you have a limited amount of subjects in the experiments. So 55 is a nice number, but in terms of being able to generalize to all the population, it's not that big. Also, there is large intersubject variability, not only because we all have different brain sizes and different shapes in the brain, and the atlas is not perfect for we are mapping to the atlas all the brains, but also because the disease develops in different way for different patients. So it's not always that it develops in exactly the same way for all of them. So there is a lot of variability there, and that's one of the most challenging things of trying to do. Yes.
Do you know if some of the healthy patients developed Parkinson's or something else afterwards?
No. The idea in the long term is to make some longitudinal studies, but in this study that I will show today, it's just a snapshot of healthy, and that's a good question. And then one other challenge with this data is that we have we can measure several trials from each subject on our experiment, but all those trials have the same label. Either the patient is a healthy control or is someone with Parkinson's disease. So we don't have the same subject in two different conditions, with and without the disease. So in this way, the characteristic of the label we want to find, that is the disease, is fundamentally linked with the variability, like the specificities of that particular subject. And we know that those can be large, so they can be, we can have a large intersubject variability. So many times what will happen is that your algorithm will end up learning who is who instead of learning things about the disease, and you have to fight against that. Like being able, if you want to generalize to unseen patients, the algorithm has to learn something about the condition and not about the particular subjects that were used for training. So in order to make a proper evaluation of how the algorithm is working, we will left 20% of the data outside the training. This is something standard on machine learning, but you can do that in different ways. So you can just don't care about if the trial belongs to subject 1 or 2, and separate 20% of the data, or you can leave out all the trials belonging to some subjects. And we are using this kind of evaluation. So we are, of all our subjects, we left out 20% and we evaluate on those that aren't seen during training. So this is testing how well you generalize to patients that subjects that are not on the training. So I will talk about now about doing this on the MEG data. So we have this 70-dimensional time series, and we want just given one trial, we want to classify. And here we have 70,000 features and only around 3,000 trials from around 40 patients, so 40 subjects. So we need a model that is capable of making a classification, but that does not overfit our data. And here it's challenging because we have a lot of features. And also we want some explainability of what's going on when the model makes this classification. So we will use a model particularly developed for time series, for being able to do this. And now I will show you the model that was successful, but we did explore. We have previous attempts to do this, and with a lot of different models, we end up classifying the subjects and not the disease. So this is something that I will show you, the one that worked, but we tried different algorithms that didn't work. So the model we are using is called Rocket, and Rocket it's basically generating a lot of different kernels and convolving those kernels with your time series. So it's a model for time series. So basically, you create some particular kernel, and you can see. So you create some kernel that you create that kernel randomly. You don't train for that. You create that kernel. You convolve that kernel with your signal. You have what we call like a feature map, and then you take some statistics of that convolution. For example, the percentage of positive values. So you count how many of those points at the lower part are positive, and you use that statistic as a feature of your signal. So the idea is that you will not train your kernels, but you will use a massive amount of those kernels. So you will have a lot of features. In this case, we are using 10,000 features. That's a common number to use, and you will stack all those features, and then train just a linear classifier on those features. So basically, this is again a kernel trick. So we will take our time series, convert that series into a series of features, and in that space, we hope that a linear classifier will be able to classify. And this model performs really well. Yes.
Yes, just to make sure, you get the different kernels, but the observable that you are computing from them, it's always the same. So you change the kernel, but you are always taking what are the, for example, these positive values. No?
Yes. Okay. Sometimes you change your bias. You randomize also which you consider positive, but yes, you always. Okay. And you can take also other statistics like the maximum value for that kernel, so you can create your features.
So it's just getting one number, let's say, for each one of the kernels, and then you have a set of many kernels, yes, in order to get this, to do the linear.
There are versions in which you can take 2 or 4 numbers, but some statistic of that, and yes, and you use.
Thanks.
Now we select this particular model because it performs really well on benchmark. So it's one of the state-of-the-art models for different benchmark in time series classification. It's relatively cheap to run because you only feed one layer, and it's harder to overfit your data with this, because if you have to fit, for example, a very deep model with millions of parameters, then you can overfit more easily. So this is nice, but the problem is that that model was intended for one-dimensional time series. Now we have a time series that is a 70-dimensional time series. So how can we deal with that? One way to do that is, okay, we can create kernels that are not like one-dimensional, but 70-dimensional and move those. But in that case, it's a combinatorial problem that went very bad to find a good kernel for that, because we have to mix all the 70-dimensional channels. So we would have to train a huge model to do that, and we cannot. And so our solution to that was, okay, let's train a particular model for each of the channels, or the dimensions. In this case, each is corresponding to a different brain region, right? Like to a different brain area. And we train a classifier for each of those brain regions. Then we will do something to select the channels, and not only select which channels are good, but also which features of those channels are good. We'll combine them and we will classify with that. So in this assumption, we are losing the ability of combining features or kernels that combine at the same time different channels, but it is feasible for us. Like we can work with this and see if this works or not. So I will go a little bit more in depth of this. So we want to classify a single trial. So first we will train a classifier for each of these brain regions, and we will rank the regions in terms of the predictive power of each of those brain regions. So what we have is something like this. We have a validation set to test how well this prediction work. And basically what we have here is, this is the 10 more significant regions for predicting. And here is the whole distribution. So basically we have a lot of brain regions that have like a chance level less or equal to 50% of ability to predict, but there are some regions that are like outliers that have good predictive ability. And those are the brain regions we are plotting here. And this is like our first important result. And this is something that we really like, because now we can point out which brain regions are important to make this classification. So looking at that single time series, we can say, we can classify. So here, this can be very informative for someone, for example, doing modeling, because if you have a whole brain model of Parkinson's disease, now you know that the activity, the average activity on that brain region should look different in the healthy controls than in the people with Parkinson's disease. And so we cannot say nothing actually of this. You cannot, yes, you can see. We cannot say nothing about this because maybe our model is not good enough. There is some feature there and we are not able to capture. But for sure, we can say that in these brain regions or these top brain regions, there is something there that is different in healthy controls and persons with the Parkinson's disease. So in this case, for example, the cerebellum is our top region, so it's the one that's the signal from cerebellum is the one that's best to make this classification. And then, for example, we have the para-hippocampus region and the medial frontal region here. So we can rank them. So let's take, for example, one of these classifiers. So let's take the cerebellum, that is the one that has the most predictive power. So now we are looking only at that particular brain region, and we develop a way in which we have trained an algorithm to classify with that brain region that is composed of 10,000 random kernels, and we have a lot of features. We have 10,000 features for that particular brain region. So what we did was develop a way in which we can address also what are the more important reasons to do that classification. So in order to do that, we normalize all the features before training our classifier. Then we train our classifier and we look at the absolute value of the weight for each of these features of the classifier. So it's very straightforward. And what we can do is to have a distribution of what are the coefficients of this. All these features have a coefficient that connect that to the prediction. So we can see that there are some features that are much more important than others to make this prediction. And we have tested this not only in this data, but on different benchmarks for time series. And it is always the case that after training, you can prune your model, you can take only some subset of features, and those features are the only important features to make the prediction. That's something that's not unexpected because we have created these features randomly. But now we have an easy way and fast way to pick the ones that are useful, and we can keep only those. And we don't lose prediction ability. Sometimes even we get a little bit of prediction. So getting rid of those noisy features. So, for example, in this case, we can take the most informative channel, the cerebellum. We only picked 5% of the features, the best features that we have randomly created. And then now we have a very small model, and we, for example, can fit something non-linear instead of a linear regression. We can fit, for example, a random forest classifier, so to get non-linear relationship about across those features. And in that case, we can have 66% of accuracy, so it's better than using the whole model, just using those 5% of features. That's and we have done this in different ways. There is a lot of room here to explore that we have not yet systematically explored, but you can take different amount of channels, different amount of features per channels, and you can select just the best channels and the best features from each channel, and you can search there what to fit on those features, but it's a way of finding good features and good channels. There is a lot of work to do. This is what we are doing right now, and but something that is really important is that here there is this is the accuracy for one single trial. It's 1 second recording of in the unseen group of patients. But we have several recordings for those because they perform this like 100 times. So basically what we can do is take all those trials for one unseen patient, and instead of classifying trials, we can aggregate that and classify the patients, the unseen patients. And so for this particular example, we had 91% of accuracy, so we can classify correctly all the unseen patients except for one. And this is basically the kind of accuracy we can get with this model to classify the unseen patients. So there is yes.
Unseen subjects.
Subjects, sorry, I say patients, unseen subjects, because in the unseen group you have healthy controls and patients. There is a lot of things to do. Now we are also developing a way of, we can rank the features, so we can look, for example, how those features looks like what's the scale, are those features selected to some particular frequency. So the idea is not only being able to classify, but also pinpoint which brain areas are important and which are those kernels, those features that are important to make the classification. So, and now we will have a little detour. We will not talk about directly brain data, but indirectly we will talk about the brain, because we will look at the at the eye tracking data. We know that eye movement, it's a window to the brain, and what's good about this is that it is much easier to record. So if we are planning, or in the long term, we want something that can have like a clinical potential to use as diagnosis or prognosis, an eye tracking machine is much more accessible than an MEG facility, for example. So we lose a little bit about learning about the mechanism in the brain, but we gain this clinical potential. So what we did was to study the eye tracking data of the experiment. So we also look at this preparatory phase. So when the subject is looking at the target, concentrating, waiting for the target to move, and this is like a whole session, and the session is like 12 consecutive trials. And basically what we are looking at is at this particular region here in green. You can see that the target moved to some place and the gaze of the person goes to the other way. So this is an anti-saccade task. And we are looking at the 1.5 seconds before that before the target moves. So it looks like the person a little bit, it has some reaction time and then go to the other way. So we'll look at this. So this is 1.5 seconds of fixation data. So the person is looking at the target. There is some mental process because they are waiting, so they are concentrated, but we have only that. And we measure X and Y position of the point to which the subjects are looking, and also X and Y velocity. We input that. So now it's and the frequency here is 300 Hertz. So now this is data that has a lot less points or features than the MEG data. So we evaluate this, we try to classify this using two different time series classification algorithms. Again, we will use Rocket, that we know that's the model that it's working well. And now we will use also a model that's more like a traditional deep model. So it's this inception time. It's a convolutional model that it's a deep model in terms that you have several blocks. So the model is very deep. And now the difference with Rocket is that the kernels that you use to make these convolutions, you learn those kernels from the training process. So it's not like Rocket that you generate your kernels randomly, but you really learn all the parameters. So this model have a lot more parameters than this Rocket model. So again, we have this patient-wise partition after doing some hyperparameter search. Here we search for different parameters for the networks and pick the best ones. And once we pick the best ones, we also perform this several times because there is a lot of randomness in the training process of how you pick your training data to train and the initial values of your parameters. So we perform this several times, and we here report the median and the standard deviation for all the times we perform this experiment. And we are able to achieve good accuracy at the trial level. And here are the confusion matrices for Rocket and inception time. In this case, inception time is working better than Rocket. But again, this is only at the trial level. We have several trials for the unseen subjects. So if we aggregate that information, so basically we took all the trials in that the subject did, then we classify each of those trials, and then we use a soft voting classifier to tell if the subject is a healthy controller or a patient. And what we get is a very good accuracy. In the case of inception time, we get 100% of accuracy on all the different realizations of the training. So it's and here we show like the confusion matrix, and also in Rocket in some of the realization we have 100%. In some others we have lower number, but it's really good also. Then we wanted to do a little bit more of exploration of these models. When we have trained the model, in this case the inception time model, we can take the last layer before the classification of the model, and we can see how the time series are represented in dots in that particular layer. And we use like a Disney projection to put that in 2 dimensions and see that there is clear separation of the trials coming from a healthy control or a person with Parkinson's disease. And if we then further segregate between saccade and anti-saccade trials and see how well we are able to predict saccade and anti-saccade, here we have better accuracy for predicting the pro-saccade trials. So this is the waiting time before they do the pro-saccade. And this is something that was for us a little surprising, because in previous studies, mainly focusing on measuring the MEG activity of the participants, at population level, the differences between healthy controls and patients were bigger in the case of the anti-saccade, and usually that was take as an indication that you are doing more effort because you want to inhibit the following of the target. So that was something that was that makes the classification easier, or you can find something that was different in both groups. In our case, it's the other way around. So this is something that's interesting for us. Yes.
What's the difference in the eye tracking data? Like, did you like the actual differences in how they?
Here we are focusing only on the preparation phase. They are looking at the target. In this case, we haven't explored like what the features that the model is using looks like. It's hard for example, inception time. It's a very deep model. It's hard to know what the model is paying attention to. But in Rocket, for sure, we have to do that. We haven't done that. We have to rank the features and see the most important features. What are those features? And that's something we have to do also for the MEG data. We can look at those filters and look what are the frequencies that are important to make the separation. That is something that we haven't still done.
But for example, I guess that as Parkinson patients have motor problems, they might have troubles to fixate on the target, and that could actually be a predictor of whether they are patient or not.
Yes, and that's something that there is a previous study that looked at again at a population level, not like a trial level or being able to make the separation between healthy control and patients, but at the population level, they were looking at, for example, the standard deviation of the gaze and those things. And yes, there is some difference there. With those features only, it's impossible to tell if someone is because you have distributions that overlap. So that was what we use in order to select this preparation phase as the input for the model. And so far, this is, to the best of our knowledge, the best algorithm so far to classify using this eye tracking data. There are other attempts in which they construct the features, like taking this standard deviation and maybe like the gaze, like the step they make when they move following the target, and they use all that as inputs to models, and they have some predictability, but we have better predictability. But the downside now is that now we cannot pinpoint which feature specifically is the one, but we want to do that study. We want to learn. Yeah. So as conclusions and things we have to do, we show that we are able to classify looking at these trials, very short trials of eye tracking and MEG data. Particularly in the MEG case, we are able to pinpoint regions that are different. The activity of those regions are different in the healthy controls and patients, and that can be informative for someone doing modeling. And then we show that the eye tracking data has clinical potential because it's easier to take. So it's easier to do these experiments, and so far we have very good results. Of course, we need to get more data and try this and other groups of participants, but it's promising. Still, we have to characterize these features. That is something that we are working right now, like how can we characterize the different kernels and the features. And we have to explore the combination of different channels and number of features, so to get which one is the best one for when we measure with the predictive power or the accuracy. And then on the long term, we want to integrate both, because we want to integrate the features from the MEG and the features from the eye tracking and see how that goes. So thanks. I want to say thank you to all the people that gave us data, to Eric, and also particularly to Simon, that it's a student that worked with us in the analysis of the data. And the part of the eye tracking data now is being reviewed. So, and I think next week will be available on archive, and we hope that the review goes well. But you can, if you want to reference, you can see this reference.
So you did the separating of the pro-saccade and the anti-saccade with the eye tracking. Did you do the same thing for the MEG data as well, where you separate out the trials to see how the classification was between those two?
No, we didn't do that with them. We have to, but we did other thing that we look at positive and negative on the anti-saccade case, like you can perform the task well or bad. So we are looking at the preparation phase. So we were interested in telling, can we predict if you are going to make an error or not? And yes, to some extent, we have like 68% of accuracy in predicting if you will make a mistake or not. And we think that it's telling us actually if you are if you have a cognitive load or not. Are you concentrated or not?
And these trials, so you said that the subjects were informed which task they would have, right?
Mm-hmm.
Did they have them like all together saccade and then all together anti-saccade, or were they mixed around?
They were all together saccade or anti-saccade in like chunks of 12 trials. Like they performed 12 consecutive trials. They were informed this is a saccade task, and then 12 trials of saccade.
Okay.
And it was not periodical the stimulus, because if not, you can look, you can wait, you know that in 1 second it will move. There was a time, so they really have to be concentrated because they don't know when the target will move.
But they still know that the next task will be a saccade one.
Yes,
Okay.
yes. And it's surprising for me that even knowing that you make errors, but even the healthy controls make a lot of errors. I mean, it's also boring. So.
Yeah.
I had a question. Like, instead of the random kernels, have you or anybody tried just using like a basis projection, like Fourier or wavelet kernels into the?
Yes, we are actually also working on that. There is a version of this algorithm. Instead of taking random kernels, you have like a dictionary of kernels that you construct given some properties of, for example, how long are your time series and some properties of the time series. You construct like a dictionary of kernels to look for. And we are actually working right now on how to do that sampling even better. Like once you train one rocket model, can you learn from the kernels which are good or bad kernels, and now select new kernels? We are doing that right now. It's something that we are working on. But it's a good question. There is better ways to sampling than random.
All right, if there are